Hello and welcome to the EMC Live webinar, Simulating Lightning and EMP Effects in Aerospace Applications. My name is Belinda Stashukevich and I'm the editor of Interference Technology, the creator of EMC Live. EMC Live is a new online 3-day event hosted by Interference Technology, featuring practical information and topics. This event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Dr. David Johns. David is the VP of Engineering at CST of America. He received his PhD from Nottingham University in the UK. David has over 25 years of experience in developing and applying electromagnetic field simulation. He specializes in EMC, EMI, and electromagnetic environmental effects applications. This webinar is sponsored by CST. CST offers accurate, efficient, computational solutions for electromagnetic design and analysis. Its user-friendly 3D EM simulation software enables you to choose the most appropriate method for the design and optimization of devices operating in a wide range of frequencies. This webinar is one of many this week. To check out our others, visit emclive2015.com. A recording of this webinar and downloadable PDFs will be available on our website shortly. This webinar will be interactive. You will be able to ask questions and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. Now David will begin the presentation.
Okay, thank you for the introduction and to Interference Technology for hosting this EMC Live event. It's my pleasure to talk on the topic of simulating lightning and EMP effects in aerospace applications today. So let's start by considering EMP. The most well-known source of EMP is by nuclear explosion. High-altitude nuclear detonation produces an immediate flux of gamma rays. These photons in turn produce high-energy free electrons by Compton scattering. The scattered electrons are trapped by and spiral around the Earth's magnetic field, which gives rise to an oscillating electric current. And this current gives rise to a rapidly rising radiated electromagnetic field called a high-altitude electromagnetic pulse, or HEMP. Because the electrons are trapped essentially simultaneously, a very large electromagnetic pulse radiates coherently. And the pulse can easily span continent-sized areas. This radiation can affect systems on land, sea, and air. But EMP can also be generated without nuclear explosion. The virtual cathode oscillator, shown on the right, is a device capable of creating a very strong pulse of EM radiation. A massive short pulse of high voltage causes the cathode to emit an intense burst of electrons by the field electron emission mechanism. The electrons are attracted to the anode, and a large proportion of the electrons pass through the anode and form a cloud behind it, forming a virtual cathode. However, the electrons are still attracted by the anode and repulsed by each other, so they change direction and fly back towards the anode, only to pass through again and be repulsed by the cathode and attracted towards the anode. So this rapidly accelerating and decelerating electrons oscillating back and forth between the real and virtual cathode through the mesh anode microwave frequencies produces the electromagnetic radiation. And CST's Particle Studio product is an ideal tool for analyzing such devices. So the physics of the EMP source region is very complex, as we've just seen. It's convenient to simplify the situation and model the EMP pulse using a double exponential mathematical function for the electric field. And this is defined in the military standards. The pulse quickly rises to a peak level of some 50,000 volts per meter in a few nanoseconds, and then decays over 100 nanoseconds or so. Fourier transformation shows that the spectrum contains significant energy below 100 megahertz. Templates are available in CST's Studio Suite to help the user get a good starting point for different kinds of simulations. The EMP template creates a model with a free space environment and a plane wave source, and the direction of the wave is easily configurable. The EMP double exponential waveform is conveniently predefined and applied to the plane wave. So in this case, we're going to show a simple example of an EMP pulse hitting a cable orientated over a ground plane. So the plane wave simulates the pulse arriving from a large distance away. The EMP waveform is sampled at time intervals and run using a transient TLM field solver. The pulses are injected as a stream of amplitude-weighted delta functions. The cable in this case is a coaxial cable, and it's approximately 2 meters long. So CST EMC Studio is an ideal tool for simulating problems like this. This software package includes CST's 3D transient solver and cable studio solver, which may be used together in a co-simulation, or essentially as a hybrid method to simulate a wide range of EMC problems. And Cable Studio enables the complexity of cables to be modeled without using a fine 3D mesh for the field solver. This hybrid approach can also be bidirectional, which means there is communication both ways between the field solver and the Cable Studio solver at every time step. So if you can imagine, the fields will be instant on the cable along the cable path. This is simulated in the 3D field solver. The Cable Studio solver takes these fields as input, and it figures out how the field couples into the cable and then sends a signal back to the 3D field solver. This kind of bidirectional coupling is critical for accurate modeling of current, return paths, re-radiation from cables, and resonant effects. One of the powerful features of direct time domain analysis is the ability to record the fields at time instances and then play back in the form of an animation. This time animation allows us to see a movie of how the pulse propagates and couples to the structure. It's possible to miss important effects when only displaying the field at certain frequencies, such as peak field levels in hotspots. Time animation gives us a more complete picture. So here you can see in the animation the field is instant at 45 degrees. It couples to the cable, and there is a reflection from the ground plane. The animation clearly shows the cable interacting with the field because of this bidirectional coupling. And you'll notice at later times the residual field is due to the cable resonating. The field distribution and current paths are actually changed by the presence of the cable, and we get these resonance effects. So the simulation is performed by setting up a transient task in CST's Design Studio tool, schematic tool. You'll notice in the circuit diagram on the right, there's no source or port in the schematic. In fact, the source is the plane wave in the 3D field solver. Coupling into the circuit is captured by co-simulation with the 3D field solver. And this allows us to calculate the currents induced on the cable, and the results show that we see some 38 amps or so peak current on the shield and around 30 milliamps peak current on the inner wire of the coax. That was a relatively simple example. Let's look at a more realistic aircraft example, such as this rotorcraft model shown in the slide. And in reality, the cable systems may be very complex. We may have hybrid cables, which include power conductors combined with signal cables. The cables may be using twisting and also overbraiding. And cables are typically routed very close to the aircraft skin, which can be challenging when meshing for simulation, because it's possible, if you're not careful, that the cable could interfere with the discretized or mesh boundary of the model. And there's a new feature in CST Studio version 2015, which allows the TLM solver to use a perfect boundary approximation, or PBA. And this enables the cable boundary relationship to be accurately maintained. So during the meshing process, the TLM mesh is warped to accurately fit the curved boundaries. In the simulation, we can place magnetic field probes in different locations. In this case, we put them near to the rotor blade hub, the top of the fuselage and below the fuselage. And these probes record the time-varying field seen at these specific locations. The time response shows some 200 amps per meter peak field strength, and some ringing in the waveform, in the time waveform, out to 1,000 nanoseconds. Fourier transform of the transient response yields the spectrum. And you can see that the ringing in the time domain is related to electromagnetic resonances. And these resonant frequencies are inversely proportional to the dimensions of the aircraft structure. So a bigger aircraft produces resonances at lower frequencies. For example, at 6 megahertz, the wavelength is 50 meters, a half wavelength is 25 meters. So if the aircraft is a multiple half wavelength, it's matching the wavelength, and this produces the resonance effect. One of the important aspects that we need to include in the model is any seams around panels or access panels, for example, as shown in the slide here on the side of the rotorcraft. And you know, it's possible that there may be cables routed directly behind those panels, and we're interested in how the seam may leak and cause coupling into the cable systems. In this case, we have a hybrid cable with power conductors and twisted wire pairs for the control wires routed just behind the access panel. This cable is unshielded, there's no overbraid. And the time response on the right-hand side shows nearly 60 amps peak current induced in the cable system. The Fourier transform spectrum shown below shows that there's a resonance at 125 megahertz. This frequency, the wavelength is 2.4 meters, so half wavelength is 1.2 meters. What's actually happening here is that the perimeter around the seam is matching a half wavelength. So the seam is actually resonating at this frequency and increasing the coupling to the inside of the aircraft. So we can also place probes, electrical magnetic probes, at any point inside the aircraft. In this case, we have recorded the electric field in the cockpit region. The time response shows very high field strength, some 35,000 volts per meter, which is not surprising because the pulse in this case is instant from above and the cockpit is essentially exposed. It has a glass canopy, but this is not a great shield to electromagnetic fields. We could use simulation to investigate conductive coating, for example, on the glass. You can see also again that there are resonances induced inside the aircraft. There's a very strong resonance at 6 megahertz due to the cavity effect inside the aircraft. If we add more detail into the model, such as bulkheads and seats and other detail, this will kind of load the cavity with losses and with kind of divide the cavity into smaller compartments, and this will have the effect of shifting resonances to higher frequencies. So this slide shows the animation of the electric field at 6 megahertz. So, you know, EMP is a broadband effect, but as we've been discussing, you know, it may induce resonances at certain frequencies. At this frequency of 6 megahertz, the airframe is behaving like a half-wave dipole. We have a strong resonance with peak electric field at the ends of the aircraft. The model that we use to simulate this uses some 3 billion mesh cells initially, but the transient TLM solver uses an automatic cell lumping process. Fine cells are retained nearby to the geometry of the model, but these are progressively lumped into coarser cells with distance away from the geometry. The net effect is that the number of cells is lumped down to 8 million, from 3 billion down to 8 million, which is a 99.7% reduction in mesh cells. So clearly this makes the computation much more efficient. In fact, we can run the model on a workstation computer and accelerate it by GPU systems to calculate a 1 microsecond response time for the EMP transient in a very reasonable runtime of about 2.5 hours. Another nice feature of this simulation is that we can display the surface current flowing on any conducting paneling of the aircraft, as shown on the left. This allows us to see any hot spots in the current and, again, to detect resonance effects. But we can also display the common mode current that is induced on the cable systems, as shown on the right. The color code is showing the intensity of the current. So red is very strong current, blue is low current. This visualization helps us to check that the model is set up correctly. You know, that the cables are attached where they were intended to be attached to the airframe, and we can visualize standing waves along the cables as associated with the resonances. and we can see the current paths that are taken through the aircraft and the harness cable systems. Okay, so that was talk about EMP, but let's move on to lightning. So we just saw that EMP is essentially a transient electromagnetic effect. Time domain codes are ideal for simulating such problems. Lightning happens to also be a transient effect, and it can also be represented by a double exponential function. For lightning, however, instead of using a plane wave, we would use a current source. That's more appropriate. And the double exponential waveform is a slower waveform. It reaches a peak level of 200,000 amps, according to the mill standard, one of the definitions in the mill standard. And this is reached in a few microseconds. With the EMP, the peak was reached in a few nanoseconds. With lightning, it's a few microseconds. So it's a lot slower waveform, which means that the spectrum contains lower frequencies, as shown on the right-hand side by the Fourier transformation. So lightning has significant energy below 30 megahertz or so. Again, a template is available in CST for lightning analysis. Lightning is really current and magnetic field dominated, corresponding to EMP, which is more electric field dominated for the coupling. So earlier on in the talk, I showed an example of EMP pulse incident on a curved cable over a ground plane. And what we've done here is reconfigure the model to simulate lightning analysis. So now we simulate the lightning event by using a vertical wire to model the lightning channel. At the top of the wire, we use a current port to inject the lightning current. The cable is a coaxial cable as before. You can see these sort of purple boundary conditions are open boundaries, which are used to truncate the modeling volume. So these absorb radiation from the lightning channel in the cable system, kind of simulating a free space environment around the system. And again, the hybrid method of combining the 3D transient TLM field solver and the Cable Studio solver in a co-simulation fashion is used to accurately simulate all the interactions. So the simulation is again launched from the schematic tool, CST Design Studio. The yellow port in the circuit picture there represents the port at the top of the wire in the 3D model. And that's where we excite the complete model. The induced current is monitored at the cable shield and the inner wire pins. The results predict some 600 amps induced on the shield and just over 140 milliamps coupled into the inner wire. Now the cable is too short compared to the wavelengths associated with lightning event to see any resonances. So you can see that the waveform essentially follows the lightning response. So time animation of the surface and wire current for the first microsecond shows the lightning pulse in the channel and the spreading of surface current over the ground plane and the induced current on the equipment boxes and cable system. Again, this kind of animation is very helpful in checking that the model is set up correctly and that the physics that we intend to simulate is also being modeled correctly. So let's now consider a more realistic lightning simulation of full aircraft analysis. And for this, we're using a model of the Airbus 400M, which is a 4-engine turboprop transport aircraft. This is quite a modern aircraft, extensively utilizes carbon fiber composite materials to reduce the weight, which is interesting from a lightning point of view, because carbon fiber composite typically has a lower electrical conductivity than aluminum. And we'll talk about this further in a moment. In the CST Studio model, we're simulating a lightning attachment to the refueling probe at the front of the aircraft. And the aircraft becomes part of the lightning channel with the current exiting at the tail. It's important to model the electromagnetic effects of the composite panels. Brute force way to do this is to model the panels as solid shapes retaining the thickness in 3D, and then apply a fine mesh to capture the current variation inside the panel. But computer resources may be quickly exhausted using this kind of approach. CST offers a more efficient approach whereby the thick panels are converted to zero thickness skins or surfaces and the physics captured using a special thin panel material model. Various options are available in the modeler to easily convert solid objects to sheets. For example, faces of solids may be selected and extracted as zero thickness sheets. This slide shows this process applied to the cockpit section. So the reason why we need to have a special model for the paneling becomes more apparent when we consider the skin effect. It is well known that current at DC uses the entire cross-section of a conductor, but it tends to move to the surface of the conductor with increasing frequency. We can define a skin depth cutoff frequency. At this cutoff, below this cutoff, the current uses the full cross-section of the conductor, but above the cutoff frequency, it becomes confined to the surface. So the cutoff frequency is inversely proportional to the electrical conductivity. Lower conductivity, as in carbon fiber, raises the skin depth cutoff frequency. This means that carbon fiber is a poorer shield than aluminum and may be more susceptible to lightning. So some examples of skin depth cutoff frequencies are given in the slide for different panel materials and thicknesses. For 1/4 millimeter aluminum, the cutoff is 23 megahertz or so. A thicker aluminum panel reduces the cutoff frequency to 14.5 kilohertz. But you can see that a 1 millimeter graphite panel has a higher cutoff than aluminum, which means that it's more susceptible to lightning. So the time domain solver, TLM solver, uses a thin panel algorithm which captures the full physics of this skin effect and diffusion process. It's a frequency dependent effect. And this is a more efficient electrical model instead of a brute force approach, just simply using a fine mesh. We validated this thin panel technique using some simple, well-defined problems. So in this case, you can see we have a multi-layer panel consisting of air, graphite, air, graphite, air, with a total thickness of 1 millimeter. And this simple case can be solved analytically to validate the 3D simulation, the TLM thin panel algorithm. And to do this, we subject the panel to an instant plane wave, and we simulate the transmitted field on the opposite side. You can see on the right-hand side in the graph plot that frequency dependency is clearly seen. The panel behaves like a low-pass filter, essentially. And there is really perfect agreement between the TLM simulation and the analytical result. So let's look at another carbon fiber composite example. Carbon fiber composite is typically formed by weaving graphite conductors, and this tends to be anisotropic. The conductivity in one direction may be very different to the conductivity in another direction, and it tends to be more conducting in the direction of the fibers. The thin panel algorithm supports this anisotropic behavior. To demonstrate this, we have subjected a composite panel which has several layers which are rotated at different angles. So you can see in the window to the left there, the laminates stack up, and you can see that the ply directions are rotating from 0 to 45 to 0 to 45 degrees and back to 0 degrees. And we subject this panel to an instant diagonally polarized plane wave. So the diagonally polarized plane wave contains both X and Y components of the field, which are equal in amplitude. We'll notice that the transmitted field on the opposite side shows that the X and Y components are different in amplitude. And this demonstrates that there's a different conductivity seen for the two orthogonal polarizations. It's also interesting that there is a phase difference between the two transmitted polarizations, and this actually leads to generation of a circular polarized wave behind the panel. We've done some more work in validating the composite panel modeling. This was some work done in collaboration with National Test Systems, NTS, and I'd like to thank Jeff Field at NTS for supporting this effort. What we did here was to look at different kinds of composite materials, a weave panel, a honeycomb sandwich, and a foam sandwich panel. We mount these panels in an aperture of a conducting wall which divides a screen room. We radiate the panels with a magnetic field from a loop antenna on one side and measure the transmission to a received loop on the opposite side. And this allows us to extract the shielding effectiveness. Here you can see the results from the simulation and the measurements for the different panel types. And several conclusions may be drawn from these results. Both simulation and measurements show that there is little shielding to low-frequency magnetic fields, as we would expect. And this is very important when considering susceptibility to lightning. Both also show increasing shielding effectiveness with frequency, and both show slightly better shielding for the foam sandwich, which has slightly thicker carbon fiber weave layers. And both the modeling and the simulation show the sandwich structures to perform better than the weave panel. In general, the simulation results show good agreement with the test data, and this confirms that the simplified equivalent thin panel carbon fiber composites models are representing reality. We've also simulated the high-frequency plane wave shielding for the composite materials. This may be more interesting for EMP, which has higher frequencies. Yeah, just a note about the test setup here. The aperture size in the screen room is about 10 inches, and the cover plate is bolted to the aperture on a 2-inch pitch. These dimensions become important at higher frequencies, as we shall see in the following slides. So here's some results for the plane wave shielding simulated with CST. First of all, we have a reference result, which is the black curve, which is just for the open aperture with no cover panel. And you can see that from 10 megahertz to 2 gigahertz, the transmitted field generally increases with frequency, which is expected because the aperture becomes electrically more significant as frequency increases. Next, we cover the aperture with a metal plate using various interface materials between the cover and the dividing wall. First of all, we use a thin sheet of plexiglass, which is used to simulate a painted lap joint. This is the result shown by the green curve. Improved attenuation or shielding is seen at low frequencies, but this degrades at high frequencies, and some resonance behavior is observed. And more about this in a moment. But then if we swap the plexiglass interface for carbon fiber composite, we can use the brute force approach to model this material just simply by using a fine mesh inside the thickness of the panel. The red curve shows the result when only one mesh cell is used in the thickness. And we can see that the result changes as we increase the mesh density to 4 cells, which is the brown curve, 8, which is the blue, and 16 mesh cells in the thickness, which is the magenta. The results are converging, but there's still some difference at high frequencies. The reason is that at high frequencies, the skin depth is very small, and a very fine mesh is needed to capture the current variation accurately. The orange curve shows the TLM thin panel model, which is in fact the most accurate solution. Unfortunately, it is also the least expensive in terms of computer resources. So this just highlights the difficulty of modeling the correct frequency dependency of composite panels by brute force meshing. You really do need a special material representation to handle this efficiently. For the plexiglass case, it's interesting to plot the field distribution in order to observe the leakage of the interface. And what we're showing here is an animation of the phase of the electric field at 940 megahertz, which is the second resonance frequency. This shows the propagating field, and you can clearly see, strong transmission through the panel. In fact, the interface looks like an antenna producing a radiated field behind the panel. If we do an animation of the field and the current at the third resonance of 1.4 gigahertz, and we can hide the metal cover and look inside the interface where the plexiglass is located. Here you can see wavelength variations in the surface current response around the interface and a clear resonance behavior. And this kind of animation is really powerful for helping you to diagnose EMC problems. In this case, helps us to actually understand the limitations of this particular test setup. Yeah, continuing on with the theme of validation, I would like to now discuss a lightning benchmark problem. So this benchmark consists of a 1.5 meter long, half meter diameter conducting cylinder, which may be either aluminum or carbon fiber with a wire mesh superimposed on it. The outer conductor is formed by a series of return conductors, and the inner conductor is the cylinder. So it's essentially like a coaxial transmission line. This return conductor technique is often used to test aircraft for lightning. A lightning waveform is injected into the cylinder, and in this case we're looking at the coupling to a wire which is routed axially down the center of the cylinder. As explained earlier, carbon fiber is more susceptible to lightning. One way to circumvent this is to incorporate wire mesh into the material to provide a conducting path for the current while keeping weight to a minimum. And the TLM solver thin panel material has the option to add wire mesh layers to the stacker. The wire mesh is modeled by defining the wire conductor dimensions and aperture size and type. The apertures may be rectangular aligned, or rectangular staggered, or circular or diamond shaped. And this special thin panel material model again avoids having to mesh the detail and makes a very difficult problem very reasonable. The wire mesh equivalent model has been validated by comparing with CST's finite element solver. In the finite element solver, a small unit cell piece of the wire mesh is modeled in detail, and the unit cell boundary conditions are used to simulate an infinite periodic structure. The transmission response for 1 millimeter size wires with 10 millimeter aperture size is plotted. And you can see very, very good agreement between the finite element simulation and the TLM thin panel equivalent model. So applying this to the lightning test cylinder, we can see how the different materials affect the coupling to the wire inside the cylinder. And you can see from the results on the right-hand side, the strongest current is seen for carbon fiber cylinder, which we would expect. The induced levels are at some 50,000 amps or so. This is the green and the orange curves. Using an aluminum cylinder brings the amplitude down to a few thousand amps, which is the blue and the red results. Finally, if we add wire mesh to the carbon fiber material, the level is reduced from 50,000 amps to similar levels to the aluminum case. We only have a simulation result for this, which is the black curve. So in addition to modeling the composite materials accurately, we also need to consider any seams or joints between panels, because this could also be a weak point in an aircraft's susceptibility. The joints may be modeled in detail using a fine mesh, but again, this would be very difficult to do this over an entire airframe. This slide shows the model of a T-joint, where the internal rib overlaps the adjoining airframe skins. We can use a more efficient approach by replacing the detail with an equivalent seam model. CST's transient solver provides a compact seam modeling feature, which enables seam paths to be selected using edges on the geometry and the seam dimensions or equivalent joint impedance specified. One example of applying this compact seam is for the gaps around the wheel wells on the Airbus 400 aircraft and the gap between the cargo loading bay doors. So edges are selected in the model and converted into these seam paths. The properties of the seam are then defined in the seam dialog, and we can either specify the physical dimensions of the seam, the gap width, the overlap distance, or the transfer impedance of the seam. And this transfer impedance relates the voltage developed across the joint to the surface current flowing over the joint. A larger transfer impedance value leads to higher coupling through the joint. As a simple test case, we modeled a typical lap joint. We modeled this in detail by modeling the two panels and the overlap and the rivets, but also replace that with the equivalent seam model to compare the results. The gap width in this case is on the order of about 8 mils, which is representing paint thickness for a painted conducting panel. And in the model, we use an instant plane wave to illuminate the scene from one side, and then we monitor the field on the opposite side. The results show the transmission from 10 megahertz to 10 gigahertz. As expected, coupling through the seam increases with frequency as the seam becomes electrically longer. A resonance occurs between 5 and 6 gigahertz or so. This is related to the distance between the rivets. The equivalent seam model shows good agreement with the detail model up to the resonance. Above the resonance, the behavior becomes more complex for the detailed real geometry because of things like the actual round shape of the rivets has some effect. So by now, you probably noticed I'm quite a big fan of field animations. Again, I think they help check that a model is behaving as expected and give good insight into the underlying coupling mechanisms in EMC problems. So in this case, you can see the surface current at the top animation at the seam resonance frequency, and it shows a standing wave along the length of the seam. Electric field animation below clearly shows the plane wave instant and leakage radiating from the seam. Okay, so we've looked at some interesting aspects such as material modeling, seam modeling, and different validation cases. Let's go back to the Airbus 400M model, where we have applied many of these modeling techniques, and we can now look at the full aircraft lighting analysis. So this can actually be solved in around 5 hours, 25 minutes using GPU acceleration, which is quite reasonable. We use the standard 200,000 amps lightning waveform, inject this into the airframe, and then we're showing here the predicted magnetic field levels, which are around 7,800 amps per meter outside the aircraft and around 1,000 amps per meter on the inside. Time animation of the surface current for the first 10 microseconds shows the current level rising and spreading over the airframe, and also shows the start of the decay of the waveform. And this kind of animation can be used to identify any hotspots. For example, at the point of the attachment on the refueling probe at the front of the aircraft, you can see the current is very high. And it's also very high at the back of the aircraft where the current bunches as it exits. We can also animate the field at specific frequencies. In this case, we're looking at the magnetic field at 1 megahertz. And this is showing how the magnetic field distributes around the lightning channel and the aircraft. So as the current flows over the airframe, it's actually diffusing through the panels to the inside because we've applied the special thin panel material model, the composites. This is in fact the main coupling mechanism. The frequencies for lightning are really too low for aperture coupling through windows. The main coupling is by current diffusion. As mentioned earlier, CST Cable Studio is ideal for modeling complex cable harnesses. The cable route is specified using curves or imported lists of coordinates, and the cable cross-sections may be defined and attached to these routes. Many different cable types can be simulated. In this case, we show a Cat5 Ethernet cable, which has 4 twisted pairs and an overbraid. Cable Studio uses a 2D field solver to extract the cable parameters and then co-simulates with 3D transient field solver. As mentioned before, we can do this in a bidirectional coupling mode. So this truly integrated approach ensures that the cable becomes part of the overall structure and it therefore affects the current paths. It also absorbs energy and it modifies any modes and resonances inside the aircraft. Cable pins may be terminated in the circuit simulation tool Design Studio, from which the entire field, cable, circuit, transient co-simulation may be controlled. So the simulation output indicates the cable pin voltages and currents. We've calculated the transient pin voltages and currents under arbitrary load conditions. Actually, in this case, we've used matched load conditions. The cable shields may be bonded to the airframe and inadvertently become part of the lightning current path. The simulation shows in this case some 80 amps induced in the overbraid of the Ethernet cable. and a few amps are developed on the inner conductors of the cable. Okay, in the last few slides, I would like to just introduce the topic of high-intensity radiated fields, or HIRF. This is also an important consideration for aircraft-related electromagnetic environmental effects. Aircraft have to fly in severe environments, electromagnetic environments, due to the man-made fields from high-power transmitters such as TV, radio, radar systems. And the spectrum ranges from 10 kilohertz to 18 or even 40 gigahertz. So in this case, we're showing an example of an Airbus A320 airliner. And you can see the model has the cockpit and passenger windows. We have a seam, the green line, showing a seam around the door, modeled using the compact seam equivalent model. And we use a plane wave to illuminate the aircraft with a HIRF field, which typically may have a 300 volt per meter level. And we can monitor the induced fields inside and outside the aircraft. We use a time domain analysis to capture the impulse response, which is shown on the top right-hand side. Fourier transformation of this response provides the spectrum. In this case, we're plotting it from 0 to 400 megahertz, which is covering the low and mid bands of HIRF. And you can see that the external field, shown in red, shows many resonances. Even at low frequencies, there are resonances. And these are the airframe resonances due to the length of the airframe. The internal field, shown in blue, is quite small at low frequencies, below, let's say, 50 megahertz or so. But at high frequencies, it may actually even exceed the external level because of cavity storage and resonance, internal resonance effects. Nice feature in the simulation is that we can mathematically integrate fields to calculate certain results. So in this case, we've integrated the magnetic field in a closed loop around the fuselage to find the bulk current. This is essentially Ampere's law, which relates the current to magnetic field. The bulk current spectrum shows a strong resonance at around 3.8 megahertz. And this is in fact the first airframe resonance where the airframe length corresponds to a half wavelength. This simulation for HIRF takes around 6 hours, 25 minutes to solve for the whole band from DC up to 400 megahertz using GPU acceleration. Okay, final slide here. I'm showing the phase animation of the electric field and surface current at different frequencies. And on the left, you can see the field at 3.8 megahertz, and you can very clearly see that the aircraft is behaving like looks like a half-wave dipole. It's a half-wave resonance where the electric field is strong at the nose and the tail of the aircraft. The bottom right-hand animation shows the field at 55 megahertz. What's really interesting here is that the seam around the door perimeter is actually resonating at this frequency, and this is increasing the coupling to the inside of the aircraft. So the perimeter around the door is equivalent to a half wavelength at this frequency. But you can also notice that there are some strong currents on the edge of the wing. You can see multiple half wavelengths along the edge of the wing, so there may be some resonance effect happening there as well. So this field and current visualization is extremely powerful for understanding the response of the aircraft to the Earth environment. Okay, I'd like to summarize the presentation. So we've seen simulation of the transient effects of EMP and lightning. Direct time domain simulation is very powerful for solving this in the time domain and capturing all the transient effects. And we can utilize efficient algorithms for critical coupling mechanisms, such as the composite materials and the seams in the cables. We also saw how broadband HIRF analysis can be simulated by calculating the impulse response of the aircraft and then using Fourier transformation to look at all the spectrum and all the resonances. Something that I've emphasized in this talk is the importance of bidirectional field cable circuit co-simulation. Tight integration of different solver technologies, or essentially hybrid techniques, allows the physics to be captured accurately, and for the cables, for example, to be really part of the system and affect the field distribution in the current paths. So we believe that this complete simulation technology by CST is ideal for simulating these kinds of lightning, EMP, and more general E3 and EMC problems. So I'd like to stop at that point and see if we have any questions.
Thank you so much, David. We've kind of run out of time for questions. If anybody has any additional questions, you can email them to us. We will pass them along to David, hopefully to be answered after when we post the video. We have received many great questions. David, thank you again for your time and expertise. Just want to let everybody know to join us next year for EMC Live 2016, which takes place next April. Attendees, if you have any questions we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website, emclive2015.com. We will also send a link to all participants shortly. Thank you for attending.